Good afternoon to one and all. I am R.V. Kiran, Assistant Professor, Department of Mechanical Engineering. So today in this video lecture, I am going to explain you about the Klein'S construction of slider crank mechanism and different terminology used in the velocity and acceleration diagrams. In the previous lecture, we have discussed some of problems in the Coriolis component of acceleration. So today we are going to extend these classes to the Klein'S construction. So our topic is the Klein'S construction. So this Klein'S construction is a simple graphical method for drawing the acceleration diagrams, and the line diagram for the mechanism is OAB, that is the triangle OAB with OA as the crank and AB as the connecting rod. So if you are going to study the slider crank mechanism, there are totally 4 links. So first link is the fixed link, second one is the crank, third one is the connecting rod, and fourth one is the slider. So these are the 4 links, and if you are going to study this slider crank mechanism, here OAB is the graphical method for the mechanism and OAB is the line diagram for the triangle. We are constructing this OA as the, and we are taking the OA as the crank here and AB as the connecting rod. So OA as the crank and AB as the connecting rod, and OB is the fixed link here. So OB is the fixed link taken here. So this is the triangle with OA being the crank and AB is the connecting rod. So we are drawing a circle with center O as and OA as radius. So OA is the crank and OA as the radius. We are drawing a circle which is, you can see in the blue color line, dotted lines, and draw a circle with center midpoint on AB to pass through the point A. Then extend the AB line to pass through the center of the first circle to locate C. So this is the AB line, and we are going to extend this line. So this is the extension line OB. So by extending this line, we can touch the center of the line, that is center of the circle of the first circle. Next, draw a circle with the center point A to pass through the C. So taking as CA as radius, draw another circle and locate the points D and E in it with a line. So locate the points D and E with a line. So this is the D point and this is the E point. So the red outline, that is OAFG, is the acceleration diagram, and OG represents the scale the acceleration of piston. So that is OG is the acceleration of piston. So G is the point for the extension of the link OA. So when you are going to extend this link OA, G point comes here. So this is the G point. So we are taking this as the G point. So this typically written as C, but this is the G point. So that is the G point. So the red line OAFG is the acceleration diagram. So this is the OAFG. So this is the acceleration diagram in which OG represents to the scale the acceleration of the piston. So here OG is the acceleration of the piston in which it ends here. That is the radius of the first circle, and OA represents the centripetal acceleration of A to O. So this is the OA line. So this OA line represents the centripetal acceleration of the point A to O. So this is the O direction. And here this triangle OAC. So this is the triangle OAC. So triangle OAC is the velocity diagram. So this consider the velocity diagram, and this OAFG. So this is the acceleration diagram. So in this triangle, it consists of both velocity diagram and the acceleration diagram. And the scale may be determined by the positions OA is equal to omega square crank radius. So that is the scale will be determined as the OA is equal to omega square crank radius. So that is the scale observed here. So the scale may be determined by the OA is equal to omega square crank radius. So OA is the crank of the first one. So next I am seeing the example problem for this Klein'S construction. So let's see an example problem for this. That is model problem. Determine the velocity and acceleration of the piston by Klein'S construction to the following specification. So we are going to draw the velocity and acceleration for Klein'S construction for the following specifications. So here the stroke is taken as 300 mm and the ratio of the length of connecting rod to the crank length is 4. Speed of the engine is determined as 300 rpm and position of the crank is 45 degrees with dead center. So I am taking it as in the dead center. So here this is the given question. So first of all, notate the points in the given data. So stroke is equal to 300 mm. So stroke is equal to 300 mm. We are taking the crank radius as half of the stroke length. So length of the crank R is taken as stroke by 2, that is 300 by 2, that is 150 mm in length. In length. And next, length of the connecting rod. So length of the connecting rod is taken as 4 into R. So 4 times the radius. So length of the connecting rod L is equal to 4R, that is 600 mm. So 4 into 150 mm, that is 600 mm. Theta is equal to 45 degrees. So theta is equal to 45 degrees and speed n is equal to 300 rpm. So speed n is equal to 300 rpm. So this is the given data, and from the speed n we are going to calculate the angular velocity, that is omega a. So angular velocity for the crank, that is OA, that is angular velocity of A, so that is 2 pi n by 60. In total we got 1.416 radians per second. So the value for the angular velocity of A is obtained as 31.416 radians per second. And next here I am taking the scaling as 1 is to 5. So 1 is to 5 is the scaling taken here. So you can take your own scaling. So scaling area తీసుకోవచ్చేమో 1 is to 10 తీసుకోవచ్చు, 1 is to 5 మీ ఇష్టం, because depending upon the purpose and usage. So here I am taking the crank length, that is the length of the crank, that is 150 mm. Total stroke is 300 mm and OA length is 150 mm, that is 150 mm. Length of the connecting rod, that is from position A to P, that is 600 mm. So in total we got 600 mm. Angular position for the crank is 45 degrees. So therefore we got the triangle PA, AO and OP. So this is the triangle. So here I am taking the crank angle as, crank length as 150 mm and the connecting rod length, that is the AP length, as 600 mm. So the length of the connecting rod is 4R, that is 600 mm. The length of crank R is 150 mm, that is AO is equal to 150 mm. Next, theta is equal to 45 degrees. So theta is taken as 45 degrees. So this is the angle 45 degrees. So from that we have obtained the circle first one, and from the center A to we have got another circle, and from the P point we are joining the O and C points. Therefore, the angular velocity is obtained as 31.416 radians per second, and triangle OAM, that is, this is the triangle OAM, triangle OAM is called as Klein's velocity diagram. So this is the Klein's velocity diagram, and OABC. So OABC is called as acceleration diagram. So OAM is the velocity diagram and OABC is the acceleration diagram for the Klein's construction. So here triangle OAM represents the Klein's velocity diagram, and the velocity of the piston is, so this is the velocity of piston is taken as velocity of P is equal to velocity of P is equal to omega into OM into scale, that is the length of OM into scale. Scaling is taken as 5 because scaling we are taking it as 1:5. So here I am taking the value as 5. So therefore omega is got the 31.416, and OM by measurement we got the length 25 and total into 5, that is 3927 millimeters per second. So 3927 millimeters per second, and by conversion 3.927 meters per second. 3.927 meters per second. So 3.927 meters per second. So here OABC is the quadrilateral. So this is the OABC quadrilateral, which is called as Klein's acceleration diagram. So Klein's constant acceleration diagram. So here OABC quadrilateral is the Klein's acceleration diagram, and acceleration of the piston AP is equal to. So this is the acceleration of piston A, that is omega square into OC into scale. So that is omega square is 31.416, and the length of OC. So this is the OC length. By measurement we got 21.5 mm, and the scaling is 5. So in total we got 1030.98 millimeter per second square. So this is the total obtained acceleration of piston A and velocity of piston. So we have defined the positions. So determine the velocity and acceleration of the piston. So మనం ఇలా డ్రా చేసుకోవాలి. సో వాళ్ళు ఇచ్చిన కన్స్ట్రక్షన్ యూనిట్ నుంచి మనం పిస్టన్ యాక్సలరేషన్ ని ఫైండ్ అవుట్ చేయాలి. సో క్రాంక్ లెంత్, క్రాంక్ యాంగిల్, నెక్స్ట్ కనెక్టింగ్ రాడ్ యొక్క లెంత్ నుంచి మనం ఈ వెలాసిటీ అండ్ యాక్సలరేషన్ డయాగ్రామ్స్ ని ఐడెంటిఫై చేస్తే ప్రాసెస్ అనేది ఈజీ అవుతుంది. సో దట్ ఈస్ ద ప్రాబ్లమ్ దేర్ for the Klein'S construction. Next one, we go to the terminology in these velocity and acceleration diagrams. So let's see some of the terminology and terms used in these velocity and acceleration diagrams. So first one is the motion. So a motion is defined as a change in position of link. So this is the change in position of the link. So a motion can be defined as the change in position of link. And in this motion, we have got two types of motion. First one is the absolute motion and second one is the relative motion. In the absolute motion, the motion is described with respect to the frame of the body. So frame of the body or mechanism. So these absolute mechanisms refers to the motion described with the respect to the frame. But coming to the relative velocity, that or relative motion, the motion is described with the respect to another moving body. That is the moving body respect to another moving body. So absolute motion and relative motion. So the motion can be divided into two types. And next one is the plane motion. So if motion, a body is said to have a plane motion if all its points move in the planes which are parallel to some reference planes. So these are parallel to the some of the reference planes. So that type of motion is called as plane motion. And next one is the translation. So a body which has translation, if it moves so that all the straight lines in the body move parallel to each other. So a body has the translatory motion if it moves to the all the straight lines in the body which moves parallel to the each other. So that is called as the translatory motion. Next one, in this translatory motion, it can be divided into two types. First one is the rectilinear translation. Second one is the curvilinear translation. In the rectilinear translation, it is a motion where in all points of the body move in straight line paths. So these all points of the body moves in the straight line paths. So that type of motion is called as rectilinear motion. Next one is the curvilinear translation. So in this curvilinear translation, it has in which points in the body move along the curved path. So these curvilinear translation has the points in the body which moves along the curved path. So that type of motion is called as curvilinear motion. That is curvilinear translation. Next one is the rotation. So all the points in your body which remains at a fixed distance from a line which is perpendicular to the plane motion. So that type of plane motion perpendicularity is called as rotation, in which the body remains at the fixed distance from a line. Next one is the translation and rotation. So a machine parts have motions which are a combination of rotation and translation. So these machine parts have the motions which are in a combination of both rotation and translation. So that is in the plane motion statistics. Next one is the spherical motion and the helical motion. So first of all we go to the spherical motion. So a point which has spherical motion, if it moves in a 3D space, so the point which has spherical motion is moving in a 3D space and remains at a fixed distance from some fixed point. So this is the spherical type of motion in which the 3D space remains at a fixed distance from the fixed point. And next one is the helical motion. So in this helical motion, the point which rotates about an axis at a fixed distance and at the same time it moves parallel to the axis which describes a helix. So these are going to be described in the helix form and at the same time it is parallel to the axis about a fixed axis, that is a fixed distance. Next one is the scalar. So scalar quantity and a vector quantity. So the scalar quantities are those which have magnitude only. So those quantities which are having only magnitude type of motion is called as scalar quantities. And then examples for the scalar quantities are distance, volume, area, and time. So distance, volume, area, and time. So these are the scalar quantities. And next one is the vector quantity. So coming to the vector quantity, this vector quantity has both magnitude and direction. So these vector quantities has both magnitude and direction. So the example for the vector quantities are displacement, velocity, acceleration, and force. So displacement, velocity, acceleration, and force. So these are the examples for variable examples for the vector quantities. And next one, addition and subtraction of the vector point. So first one is the addition vectors. So in these addition vectors, it transfers the positive element to the next element. So that is a plus to the b point, that is positive form of point to the next point, that is the b point. But in the subtraction vector, it is transferring only the common type of element to the next one, that is subtraction of b from a, that is subtraction of b from a. But here it is adding, that is a plus b and here b minus a, that is the in the subtraction vector. Next one, velocity. So velocity is the rate of change of displacement. So it is the rate of change of displacement in the position. And first one is the linear velocity. So rate of change of linear displacement. So the linear velocity is termed as rate of change of linear displacement, that is equal to ds by dt. It is transferred in the units meters per second. So rate of change of linear displacement is taken as ds by dt, that is meters per second. The next one is the angular velocity. So angular velocity may be defined as rate of change of angular displacement. So rate of change of angular displacement, it is denoted by d theta by dt, and units are radians per second. Radians per second. Next one is the relation between these linear velocity and angular velocity, that is taken as omega is equal to v by r. Omega is equal to v by r, that is velocity by r. And this velocity is equal to radius. So velocity is equal to r, that is v is equal to r, and omega is defined as v by r. So that is the relation between linear velocity and angular velocity. Next one is the absolute velocity. So the velocity of a point or body relative to the frame, that is the VA. So velocity of a point, it is called as absolute velocity, in which the velocity of a point or body is relative to the frame. Next one, it is the relative velocity. So the velocity of a point or body which is relative another moving point or body, it is taken as velocity of AB. It is taken as velocity of AB. So these are the different types of terms. Next, going to the last slide is the terms, that is the acceleration. So acceleration is the time rate change of velocity. So it is the time rate change of the velocity, and in the acceleration it is divided into two types, that is linear acceleration and angular acceleration. So linear acceleration is denoted in the terms a, and angular acceleration is denoted in the terms alpha. So for the linear acceleration, it is the time rate of change of linear velocity. So that is the time in which rate of change of linear velocity. It is denoted by small a, and it can be written as a is equal to dv by dt. That is, we can also take it as d square s by dt square meters per second square. So it is taken as A is equal to dv by dt. It can also be written as d square plus by dt square meters per second square. And next one is the angular acceleration. So it is the time rate of change of angular velocity, that is alpha. So it is denoted by the letter alpha. Alpha is equal to d omega by dt. So it is taken as d omega by dt, and it also can be written as d square theta by d theta, sorry, d square theta by dt square radians per second square. And next one, it has the normal and tangential accelerations and the relative acceleration. First one is the normal acceleration and the tangential acceleration. So the normal acceleration, coming to the normal acceleration, it is the due to the change of magnitude, but not to the direction. It is only due to the change of magnitude, but it has the point curvilinear motion in which it has the normal acceleration resulting from a change in of direction. So that is the change in direction of its linear velocity. That is A of n is v square by r. A of n is taken as v square by r. We can also take it as omega square r. Also get written as omega square r. Next one is the tangential acceleration. So this tangential acceleration is due to the change in the direction of velocity, but normal acceleration is change in the magnitude only, but it is the change in direction of velocity. And if the direction of its linear velocity changes, then the point will have a tangential acceleration. So this point has a tangential acceleration with respect to the tangential, that is linear velocity. So if the direction of its linear velocity changing a point will help to tangential acceleration, it is called as tangential acceleration. So TA, that is tangential acceleration, is taken as alpha into r. So alpha means angular acceleration, r means the radius. Coming to the last one, that is relative acceleration. So relative acceleration is taken as, that is ABA is equal to, so ABA is equal to AN into BA plus AT into BA. So AN is the normal acceleration and AT is the tangential acceleration of the links BA. So the relative acceleration of the acceleration BA is equal to normal acceleration of the BA link plus tangential acceleration of the BA link. So these are all the different terminology used in the velocity and acceleration diagrams. And in this velocity analysis, three types of methods has been extensively used. First one is the graphical method. Second one is the relative velocity method, and third one is the instantaneous method. So three types of methods have been used. So in the graphical method, we are going to draw the velocity diagrams and the acceleration diagrams. But in the relative velocity method, we are going to use it in the velocity methods only, that is in the velocity diagrams only. Next one is the instantaneous method. So that is the three methods. So the main one is the graphical method. So first we can see the consideration points of the procedure. So first one is the graphical method, first and final method, and later we can see the instantaneous method. So in the graphical method, the following points are to be considered while solving the problems by this method. So the following points are to be considered while solving problems by this method. And first point, draw the configuration designed to a suitable skull. So we are going to draw the configuration of total elements to a suitable scale, and then we are going to locate the all the fixed points in a mechanism and taking the fixed points as a common point in the velocity diagram. So for suppose AB is the fixed point, so the 2 points A and B is taken as 1 point in the velocity diagram. So we have already seen that, and choose a suitable scale for the vector diagram velocity. Then we are going to choose a suitable scale for the vector diagram velocity, and then the vector velocity vector of each rotating link is omega r to the link. So the velocity vector can be taken as the each rotating link, that is omega r to the link. Next, velocity of each link in the mechanism has both magnitude and direction, and we are going to start from a point whose magnitude and direction is unknown, that is known, and the point of velocity diagrams are indicated by small letters only. So these velocity diagrams has been indicated with the small letters only. So these are the procedure for this velocity analysis, that of graphical method. So by this, I am ending this video lecture. In the next class, we are going to discuss more models. Thank you.